Next up, we've got the rational root theorem. Here you've got to identify some possible rational roots and then do some dividing in order to factor. I'm going to talk about a couple different ways that you might do the factoring part, but let's start by identifying good guesses. For these, we could do some fractional ones. In this one, you don't need to because the beginning is a 1. But we're just going to identify factors of 10. And when we do that, that's going to be 1 and negative 1, 2 and negative 2, 3 doesn't work, 4 doesn't work, 5 and negative 5, 6 doesn't work, 7 doesn't work, 8 doesn't work, 9 doesn't work, and then we got 10 and negative 10. If it helps you, you could also write these as factors, although you certainly don't have to. That'd be x minus 1 and x plus 1. That'd be x minus 2 and x plus 2. That'd be x minus 5 and x plus 5. And that would be x minus 10 and x plus 10. I'm okay with you writing these in either format, as factors or as roots, or if you'd like to write both, that's okay too. I recommend that you write them separately for the pluses and minuses just because it makes it a little bit easier. I don't really know where to begin with this, so I might try to begin with a smallish number. Maybe I'll try with x minus 1 because that's the first thing I see here. That means that plus 1 is going to go outside, and inside we're going to have 1, negative 6, 3, and 10. I'm going to bring down my 1, and when I do that, we multiply to get 1, we add to get negative 5. We multiply to get negative 5, we add to get negative 2, we multiply to get negative 2, and we add to get 8. 1 does not work. I did not get 0 at the end. That means that that is not possibly a factor for us. The next one I might try, I don't know, maybe x minus 2, which means I'm going to put a 2 out front. 1, negative 6, 3, and 10. 1 comes down. 2, negative 4, negative 8, negative 5, negative 10, and 0. So second try, that's not bad. In fact, that's pretty good for these things. And I could handle this a couple different ways. What I think is the easiest approach based on the stuff that we've done this year is to factor this. This would be 1x squared minus 4x minus 5. And I know some of you disagree about the easiness of factoring, but that's okay. So we've got 8 times c is negative 5, b is negative 4. That's going to be negative 5 and positive 1. So we'd have x minus 5 and x plus 1. Okay, looking at what we've got inside of our parentheses, the first one I'm going to put is going to be x minus 2. That's why I divided by. The next one I'm going to put is going to be x minus 5. And the last one is going to be x plus 1. If you hate to factoring, there's an alternative way to do this. And that's taking the values that we have here and starting dividing using those. So 1, negative 4, and negative 5. Based on our new last number is negative 5, the only numbers to try would be 1 and 5. We already tried x minus 1, that didn't work. So let's try x plus 1, which is minus 1 here. 1, negative 1, negative 5, positive 5, and 0. That gets us that same x plus 1 and that same x minus 5 without actually having to factor. If you prefer doing synthetic division, and I know that some of you do, that would be a way to avoid factoring. The last part, identify all zeros. Once you have the factors, these would be the numbers that make each of those parentheses equal to 0. So x equals 2, x equals 5, and x equals negative 1. Hey kiddos, here's a spiral review for spiral 16. I'm going to start off with the rational root theorem. This is going to be the last time that we see this topic. For the first part of this, we got to identify all possible rational roots. I gave you some nice, easy numbers to work with, like 120, which totally doesn't have a billion roots, or maybe it does. That's going to be plus or minus 1. And with that, that would be plus or minus 120. Plus or minus 2 would also work. And plus or minus 60, plus or minus 3, and plus or minus 40, plus or minus 4, and plus or minus 30. 5 works, oh, this is fun. Plus or minus 5, and plus or minus 24. 6 works, plus or minus 6, plus or minus 20. I'd like you to notice that things are kind of merging together. Slowly, but they're getting there. 8's going to work. 7 does not. Plus or minus 8 and plus or minus 15. 9 does not work. 10 works, and that gives us plus or minus 10 and plus or minus 12. And 11 does not work. That gives us a total of 16 different numbers, and if we include the positives and negatives, we're at 32 different choices. Wow, this seems super pleasant. But let's just start dividing. I want to do this in a really organized way, so I'm going to start with 1s or 2s, maybe just 1s. So if that's going to be x minus 1 to give me a positive 1, we're going to have 1, 5, negative 26, and negative 120. All right, bring the 1 down, multiply, we get 1, add, we get 6, multiply, we get 6, that gives us negative 20, and negative 20, which gives us negative 140. Not anywhere close. Okay, so 1 didn't work. I also noticed that none of these numbers, like this just kept getting worse. And I might switch to 2 to see if I can make those differences get any smaller. So 2 would be x minus 2. Same thing, 1, 5, negative 26, negative 120. We get 1, we're going to have 2. That's a 2, okay. Then 7. 14, and that's going to be negative 12. 2 times negative 12 is negative 24, and that does not get me anywhere close. That's even worse, negative 144. I'm going to kind of keep going up and maybe see if I can make some grounds here. This is, I've gotten 2 that didn't work already. I don't know, maybe I'll even jump to like 6 or something. I realized that I said I was going to do some kind of an organized method, and I'm definitely not doing that right now because I'm in the mode of I don't really know what to do, so I'm going to keep trying things. So 1, 5, negative 26, negative 120. 1, 6, 11, 66. Oh, this is looking more promising. I'm getting weird things going on here. And that's going to be 40, and 6 times 40 is 240, and that still gives me something that doesn't work, but now my numbers are really big. Maybe I'll try to go somewhere between those things, like with 3, and we got x minus 3, and 1, 5, negative 26, negative 120. 1, we get 3, 8, we get 24, negative 2, and that's going to give us negative 6, which does not give us 0. Oh, this is going so well. I guess maybe that's those are closer numbers to what we're looking for. Maybe try 4. And let's put the L on the wrong side. So we got 1, 5, negative 26, and negative 120. That gives me 1, 4, 9, 36, That's going to give me 10 and 40, and none of these are working. I guess the only number I haven't tried in this range is going to be 5, and if this doesn't work, we have to have a new system of attack, maybe go after those negatives that I've been avoiding. So that's x minus 5 would give us 5, 1, 5, negative 20, and negative 26, and negative 120. That's going to be 1, 5, 10, 50, 24, 120, and 0. Wow, on the 6th try we got that. So that means 1x squared plus 10x plus 24. A times c is going to be 24 with a b of 10. That's going to be 6 and 4. So my first one from that equation was x minus 5. That's going to give us x plus 6 and x plus 4. So we're going to have zeros of 5, negative 6, and negative 4. And looking at those two numbers, I understand now why we didn't get an answer. We were only trying the positive ones, and the two that we did not get to by trial and error were both negative values. And finally, we got the new stuff. Here we've got rational functions. The first part, we're describing the behavior of rational functions, and for the second part, we're going to be sketching a graph. First off, we've got some end behavior pieces. This is as x approaches negative infinity. That means we're going to the left. So I'm going to look at my graph going to the left. It looks like we're approaching a height of 1 on our graph. So I'm going to say y approaches 1. And for the next one, going to the right, on our graph on the right side, we're approaching, it looks like the same value. We can't see a lot of this graph because I wanted us to see the behavior at the middle pretty well. But this would be approaching 1 as well. That's a horizontal asymptote. And if you have a horizontal asymptote that's equal to 1, both of these end behavior values are going to end up being 1 as well. That means we're approaching 1 on both sides. The other part of this is about the asymptote. As x approaches negative 2, oh, that's totally supposed to be positive 2. That's fun. From the right. So now we're talking about this side. That little plus means from the right. And as we approach this from the right side, it looks like our graph is going down. And down would be negative infinity. Same thing for the other part. From the left side, this minus means from the left. Our graph is going up. So we're looking at a positive infinity. I also just want to mention on the next version of this problem, here, this is an oblique asymptote. It doesn't approach a value on both sides. It keeps going up and keeps going down. So on the left, we're going down. That means that that would be negative infinity. And on the right, we're going up. That would be positive infinity. The other part's really similar to what we did before, so I'm not going to go through that. Let's talk about graphing. There are no numbers in this spiral. This is super fun. X plus 2 over x minus 3. For the vertical asymptote, that's going to be whatever makes the bottom equal to 0. So x minus 3 is equal to 0. That means that x is equal to 3. So I'm going to have 3 on my graph and a nice vertical dashed line to show that off. For the horizontal asymptote, I'm going to use the ratio of my leading coefficients because we're talking about when x gets wicked big, which means the other pieces don't matter. And if I've got 1x over 1x, that's equal to 1. Y equals 1 would be my horizontal asymptote. So I might do a nice horizontal dashed line, identify that as a height of 1. For the x-intercept, we said that's when y is equal to 0, but the shortcut is just looking at the top of this. If x plus 2 is equal to 0, x equals -2 is my y-intercept. And I like how I was talking about x-intercepts, but just said y-intercept, sorry. And then finally, we're looking at the y-intercept this time. I'm really talking about that. That's when x is equal to 0. So I'm going to plug that in. We get 0 plus 2 over 0 minus 3. And that's going to be y is equal to -2 over 3. And again, all you need to do is to identify that point. And I'm not going to give you a grid, so you don't really need to worry about getting that exactly right. The last piece is to draw a nice smooth curve. I know I've got to connect these 2 points, and my graph's got to look something like this. Some of us call this a weird C or a funky L. Either of those are okay. And we're going to have the other half in the opposite corner, so something like this. I am also going to graph the second one of these because I'd like us to talk about the transformation here. Here we've got a mother function that's centered at 0, 0. This would mean that we're going right 3 and up 2. And what I'd like us to also think about that is that the horizontal asymptotes and vertical asymptotes are moving as well. So for the vertical asymptote, it's going to start at 0, go right 3, or you think about what would cause us to divide by 0, and that's going to be x equals 3. The horizontal asymptote is going to be based on moving up 2 from 0. That gives us a y is equal to 2. These forms of equations are really easy to find the asymptotes for, but a little bit harder to find the x and y intercepts for. In fact, finding the x-intercepts, some of you might call a force. So let's do the y-intercept first. We know that's going to be based on when I plug x equals 0 in. So 1 over 0 minus 3 plus 2 is going to be about 1.7. So a y-intercept of 1.7-ish is going to be here. For the x-intercept, we're going to start out with 0 is equal to 1 over x minus 3 plus 2. -2 is equal to 1 over x minus 3. I'm going to continue this work over here. I'm going to multiply both sides by x minus 3, and I get -2 times x minus 3 is equal to 1, which means we've got -2x plus 6 is equal to 1. -2x is equal to -5, and x is equal to positive 2.5. With the same type of thing we had in the last one, where we have 2 points on one side, and the opposite corner would have the other side of that graph. Next up, we've got some rational expressions. The first thing we got to do is factor and then identify some excluded values, and then finally do some reducing if we can. Both the top and the bottom of this are factorable. For the top, if I do a times c is going to be 7, which means we got a b of -8. Looking for things that add up to -8, multiply to 7, that's going to be -7, -1. Since we have a 1 out front, we can use the shortcut, x minus 7 and x minus 1. On the bottom, we're going to have a times c is going to be -1, b is going to be 0 because there's no x term. Things that multiply to -1 and add up to 0 are going to be -1 and positive 1. You might also notice that this is the difference of two squares, and that's going to be the square root of x squared, which is x, and then the square root of 1 is 1. We're going to do a +1 and a -1. Same two values that we got here. Next up, we got our excluded values. Whatever would make the denominator equal to 0, so in this case, x plus 1 cannot equal 0, which means that x cannot equal -1, and x minus 1 cannot equal 0, which means that x cannot equal positive 1. Big idea here is that we only look for excluded values in the denominator. We don't care about the numerator at all. These are just places that we're dividing by 0. And then finally, I'm going to cancel out my x minus 1s, leaving me with the final answer of x minus 7 over x plus 1. Moving on to 1 with some division, we're going to start this off the same way. I've set these up so you don't have to check for excluded values twice, but with division often you do. But let's go piece by piece and factor this. First term, we can take a 2 out of both of those. I've got 2 and then x minus 2. On the bottom of this, I can take a 3 out of both of those. That would give me a 3 and then a 2x plus 3. And then on this side, I'm going to keep my divide for a minute. 2 can't do anything, so I'm going to leave that as just 2. And on the bottom, this is going to factor into x plus 3 and x minus 3. That's a difference of 2 squares, so we're always going to have the same factoring pattern. And I have a feeling this is going to be one of the ones that I didn't do the math right in my head, and something's not going to cancel out that I was planning on canceling out, which is okay. Okay, let's find some excluded values. 2x plus 3 cannot be 0. That means that negative 3 cannot be 2x. And that x cannot be negative 3 over 2. Next up, we've got x plus 3 cannot be 0, which means that x cannot be negative 3. And then finally, we've got x minus 3 cannot be 0, and x cannot be positive 3. All right, now I've got to deal with the divide. I know that I keep the first part the same, so 2 over x minus 2 over 3 times 2x plus 3. Change this to a multiplication, then we're going to make this the reciprocal. We get 2 on the bottom, and we get x plus 3 and x minus 3. Cancel out my 2's. That's the only thing in this problem that can cancel out, because I was planning to do some other stuff, and then I think I just made that a 6 instead of a 3, but that's okay. So our final answer is actually going to be x minus 2 times x plus 3 times x minus 3, and then on the bottom, 3 and 2x plus 3. Nothing else to cancel. That's it. Finally, for this section, we're going to look at a multiplication problem, starting exactly the same way with some factoring. And the first part is going to factor into x minus 2 and x minus 3, things that multiply to 6 and add up to negative 5. For the bottom part, both of these have an x in it. That's x and x minus 1. For the next part, nothing factors there. And then I can take a 3 out of both of those, so 3 times x minus 2. Okay, exclude values next before I start canceling. And I've got x cannot equal 0. I'm going to have x cannot equal 1, and I'm going to have x cannot equal 2. I don't need to deal with 3 because that's a number, and 3 can never be 0, so there's no reason to include something regarding that. Okay, finally doing some canceling. I've got an x minus 2 on the top and the bottom. Those go away. I've also got an x on the top and the bottom. Those go away as well. And we're left with x minus 3 times 2 on top. You can put that 2 out front if you want. And the bottom we got x minus 1 times 3. And then finally we've got to solve some equations. This is the new stuff for this cycle. The first one we got to do some factoring. We're going to find some excluded values. Hey, this sounds really familiar. And then solve that equation out. At first, I've got difference of 2 squares. That's going to be 1 over x plus 3 and x minus 3 plus 2 over x minus 3. I'm going to leave a little bit of space because I know I'm going to have to find some common denominators. And 4 over x plus 3. Okay, excluded values. I know that for this, x cannot be negative 3, and x cannot be positive 3. So if I happen to get one of those answers that can't work for this problem, I'm trying not to make those, but if I do things on the fly, which this problem was made, that sometimes happens. Okay, I'm going to try to get the same denominator in all three of my fractions. So I'm going to look for x plus 3's. My second fraction does not have that, so we need an x plus 3 over an x plus 3. And now I'm going to look for x minus 3's. My second one has that, but my third does not. And by the way, my third does have an x plus 3. So we're going to have an x minus 3 there, and an x minus 3 there. That's going to give us something that, if you'd like to think about this as 1 plus 2x plus 3 is equal to 4 times the quantity x minus 3. And all of those are over the same denominator. We talked a little bit in class about if you ever get the denominators to all be exactly the same, you can entirely eliminate them from the problem, which will leave you with 1 plus 2 times the quantity x plus 3 is equal to 4 times the quantity x minus 3. So that's 1 plus 2x plus 6, doing some distribution, is equal to 4x minus 12. I'm going to minus 2x to both sides to get a 2x there. 1 plus 6 is 7. I'm going to add 12 to get 19. We get x is equal to 19 over 2. Since 19 over 2 is not one of my excluded values, we are okay. I wasn't meaning accidentally giving you a problem that doesn't work out right. All right, for the next one that is marked as a video, this one's set up a little bit easier for us. I'm going to start with factoring, nothing to factor. Excluded values are going to be, based on the denominators, x cannot be negative 2, x cannot be negative 3. So I'm going to multiply both sides by both denominators to kind of get these things started. We're going to multiply by x plus 3. I'm going to, ooh, that was a fun shape. I have no idea what caused that. I'm going to undo that. Zoom out, or, ooh, that also disconnected some things. That's interesting. Okay, well, I'm going to multiply this by x plus 3 as well, because apparently I can't move my page. On the right side, those cancel out. And on the left side, that's going to end up giving us something to distribute. I'm also going to multiply by x plus 2 on both sides, and using my terrible notation because things are not moving the way I want them to, we're going to have things kind of stacked. On the left side, those cancel out, and on the right side, that gives us something to distribute to. So on the left, we've got x squared plus 3x. On the right side, we're going to have 4x plus 8. And in order to try to solve this, I'm going to bring everything over to one side. So we've got x squared minus 1x and minus 8. I'm already going to see that this is not factorable, so you'd have to use the quadratic formula, which was not my intent. And again, this is what happens if I make problems up on the fly. I actually thought that I had nailed this one and gave you one that was totally factorable, but apparently I did not. So I'm sorry for that. We're not going to finish solving this. You'd have to solve for both values and check to see if they didn't work. And again, not my intent here. The one for your spiral I'm going to build a little bit differently so you don't have to worry about this showing up. Next up, we've got to solve some rational equations, and we're going to start off with number 9. The very first thing I'm going to do, because I'm confused having a 3 over here, is I'm going to make that into 3 over 1. So now we are indeed all fractionified. The second thing I'm going to do, I really like the finding common denominator method of this. Nothing is factorable here. I do have to find excluded values. I'm using the checklist that you can't see below me, so I know that x minus 2 cannot equal 0. I did not do this out ahead of time, so I don't know if we're going to get that as an answer. I hope not. But then we got to find some common denominators. I know that I've got a 3 and an x minus 2. I don't need to worry about the 1. For the first fraction, which is 1/3, it needs an x minus 2. So I'm going to multiply the top and the bottom by that. For the second fraction, oops, I am going to make that a plus. Put a minus 2 on top. That makes me less likely to make a mistake, although for this one it's actually a little bit easier because it's just a number. And we're going to have to, so that's x minus 2 already on the bottom. So we need times 3 and times 3 on top. Okay, then we've got equals. 3 over 1 has neither 3, so it needs to be times 3, or the x minus 2, so it needs an x minus 2 as well. Wonderful. Let's do some simplifying. I'd like you to notice that all of my denominators are now the same. I can now ignore them. For the first one, we've got 1 times x minus 2, which is just x minus 2. For the second one, we've got negative 2 times 3, which is minus 6. And then on the side, 3 times 3 is 9. 9 times x minus 2 would be 9x minus 18. I'm going to bring the 18 to one side and combine some stuff. Negative 2 minus 6 is going to be minus 8. I'm just going to rewrite this before I start combining things. I'm going to add 18 to both sides, leave me with 10. Minus x from both sides, leave me with 8x. And when I solve that, I get x is equal to 10 over 8, or if you'd prefer, 5 over 4, or 1.25. And that is not 2, which was our excluded value. That I don't think we actually ever finished solving up here. So we're actually in pretty good shape there. For number 10, we've got 3 over x squared minus 4, and we've got x minus 2x plus 2. I've given you a hint that if you have fractions like this, that means you can use the other pieces to figure out what you should factor into. But if you didn't get that hint, this is difference of 2 squares, and x squared minus 4 factors into x plus 2, and x minus 2. The nice thing about that is that now we've got 2 over x minus 2. I'm going to leave some space. I know I'm going to have to do some common denominators. And 3 over x plus 2. I know that I've got to have an x plus 2 in everything, so we've got that there. Now we're good here, and we already have it over there. I also need an x minus 2 in everything. We're good on the left side, so we need an x minus 2. And we know that if we do that in the bottom, we got to do that in the top, and I missed doing that on my x plus 2, so I'll put that in now. All denominators are exactly the same. We're going to cross them out. On the left side, we got 3. On the right side, we've got 2 times x plus 2, which is 2x plus 4. That's doing some distribution. And then we've got 3 times x minus 2, which is 3x and minus 6. All right, on the right side, we're going to have 5x minus 2. And on the left side, we've got 3. I'm going to add 2 to make 5 is equal to 5x, which means that x is 1. And I have no idea if this actually works because we forgot to do excluded values. Oh, no. So we're going to have x minus 2 cannot be 0. We're going to have x plus 2 cannot be 0. And that means that x cannot be plus or minus 2, which thankfully is not 1. So that one is actually all set too. All right, to the last page, and here we've got radical equations and graphs. This is our new section. This is the feedback section for this. The first thing we got to do is deal with some graphing stuff, and I did the video for the first one. So here we've got the equation of y equals the square root of x. That came out kind of funny looking, so I'm going to cover that. Radical, okay, that looks even worse, but that's fine. And we got to do some transformations. I've got 3 transformations going on here. This is a vertical stretch with a height of 4, so I'm going to write that here. So vertical stretch times 4. Really what that's going to look at is when you go 1 over, instead of going 1 up, now we're going to go 4 up. So that's the first piece we're going to play with. The second one is on the inside. This is going to be a horizontal flip. Actually going to do that part first so that we have something a little bit clearer to work with. And then finally, we were going to have plus 2 at the end. It's going to slide up 2. So if we were to combine these three things, we know this is going to be going backwards instead of forwards. It's going to be starting from up 2, so I'm going to take my 0 point and slide that up 2. I know that the vertical stretch times 4, instead of going up 1 over 1 to here, it would go up 4 over 1, but again, we're going to flip back the opposite way, so it's going to be flipped into the opposite side of things. If you really wanted a third point, the next one was at over 3 and up 1. Now it's going to be at back 3, 1, 2, 3, and up 4 more, 1, 2, 3, 4. And give us something that looks like this. Oh, heck, I might as well do number 14 as well. So here we're looking at a cube root function. And here we've got 3 transformations again. This is going to be going right 2, that comes from the inside, up 1 from the outside. It's going to be a vertical flip. So it's going to be upside down compared to this, and then times 3 for a vertical stretch. So just kind of looking at this, we've got some basic points at 0, 0, 1, 1, and -1, -1. And if we go, I'm always going to start with this inflection point. Over 2 and up 1, the new inflection point is going to be here. So that was this point. From here, I'm going to really just use this -3 to kind of help me figure out what's going on. This one used to be over 1, up 1. Now it's going to be over 1, down 3. This other point used to be down 1, back 1. Now it's going to be back 1 and up 3. So that my graph looks something like this. That's about as accurate as you need for any of these problems. The final part for 13 is finding the domain of this guy. I'm going to use the graph for that. My graph starts at 0 and goes to the left, so I could say that x is less than 0. Or if I want to use interval notation, I could say this is from -infinity to 0. Or I guess that would be less than or equals. Or x is all values less than 0. Anything like that makes sense. That's only where that graph shows up. For the range, we're going to look at the y value and go up from there. And it looks like we start at 2, and y would be greater than or equal to 2. Or if you want to use interval notation, it would be 2 to infinity. All right, number 16. We got to solve this equation. We've already got the square root by itself, so we know we got to square both sides. We got x squared is equal to x plus 2. We are going to have to look for extraneous values, and that's because we had a variable on this side. Whenever we have a variable over there, we will have to do this. I've also got an x squared and an x in the same problem. So I want to bring everything to one side, and that's going to give me x squared minus 1x. I'm going to put that coefficient there to make it easy to see. Minus 2 is equal to 0. This is factorable using a times c factoring. This is going to come out as x minus 2 and x plus 1. All right, and that's still equal to 0, so that gives me x minus 2 is equal to 0, or x equals 2, and x plus 1 is equal to 0, or x equals 1. Sorry, x equals -1. Woof, that's weird. So let's plug these numbers in and see which ones work. If I plug 2 in, we get 2 is equal to the square root of 2 plus 2. 2 plus 2 is 4. The square root is 2. That one works. If I plug -1, we get -1 is equal to the square root of -1 plus 2. And you might notice that here we have a positive square root and a negative value. that means that this does not work, that this value is extraneous. I am going to finish solving this just to kind of show us this, so that if you're not seeing that, that's okay. So here we get -1 is equal to the square root of 1. -1 is equal to 1, and that does not make sense. That's not true. And when we have a not true answer, that's when it's an extraneous solution. All right, next up we're doing number 11. Here we've got the mother function for y is equal to the square root of x, and you're asked to do some transformations. In fact, we're asked to do a whole bunch of transformations here. I'm going to find my horizontal and vertical flips first. I've got a negative out front. That means I'm going to be flipping down. And I've got a negative on the inside. That means the shape of my graph, instead of going up and to the right, is going to be going down to the left. So it's flipping both ways. Now that I've found that, let's find the vertex, which starts at 0, 0. It's going to be going right 1. I'm just going to do this as an arrow. And it's going to be going up 4. So from 0, 0, going right 1, up 4. And that's my point. And then finally, I'm going to use this -3, which means I'm going to be going down 3 over 1. But to get this shape, I've got to go down 3 and back 1. So we have a graph that looks something like this. For the domain, we don't have a starting point. This time we have an ending point. And this is at 1, 4. So x is going to be less than 4. In fact, it's less than or equal to 4. If you'd prefer the notation using intervals, that'd be -infinity to 4. But all you have to do is talk about x being less than 4. Similarly, the range, and I like how I wrote 4, but that's actually 1. Oof. It's because 1 is the x value there. So the range is going down from 4. So we're talking about y in 4, and if y is less than or equal to 4, that's when we go down. Here the range would be -infinity to 4. I didn't mark either of these as video problems, but I'll do number 12. Here we have a radical already by itself. Let's square both sides. And by the way, since their x is being squared, we are going to have to check for extraneous solutions. That gives us x squared is equal to x plus 2. Bring everything over to one side. We get x squared minus x minus 2. And that's going to factor nicely for us. By the way, that's equal to 0. That's going to factor into x minus 2 and x plus 1, which gives us x is equal to 2 and x is equal to -1 as our answers. If I plug 2 in, we get 2 is equal to the square root of 2 plus 2, which means that 2 is equal to 2. We're good. If I plug -1 in, we get -1 is equal to the square root of -1 plus 2. -1 is equal to the square root of 1, which is not true. -1 is extraneous. Therefore, x equals 2 is our only answer. You do have to show that you got that answer and checked it in order to get credit for that. And then finally, we got the new stuff. This is dealing with rational exponents. We're going to start off by doing some converting. And here we've got to convert from radical to rational exponent form. What I'd like to remind you is that this is going to be the numerator. I'm not going to use n for that because I use n for the index. So whatever I end up on the inside, we'll talk about that in a second. We're going to have a fraction here. 6 is going to be that numerator. The index is the denominator. And the stuff on the inside is always going to be that base. That's it for this problem. All you're doing is converting that. For number 16, we're going backwards. And we got a couple things we got to be aware of. The first is that this is going to be some kind of a radical, and that the inside is going to be inside this radical as well. And actually, I'm going to take a step back to talk about this for a second. You need these parentheses. If you do not have these parentheses, the 6 over 5 only goes with the x. so you need the parentheses around that whole thing. Going backwards, we tend to not have that issue as much, depending on how you write this, because we have the radical that acts as a grouping symbol for us. We know that the numerator here becomes the power here. If you put this on the outside, you don't have to worry about parentheses. The denominator here becomes the index here. Denominator of 2 means that this would be an index of 2. However, 2 would be a square root. So we've got 2p to the 3. And when we do that, you're good. You could also leave it with the index there. It doesn't really matter for square roots. For the next one, number 18, we got to reduce this radical expression. And when we do this, I'm going to factor the beginning part into everything that I can multiply to get to 18. I know that's going to be 3 times 6, but 6 could be 3 times 2. And I also know x squared is x times x. What this tells me is I've got a pair of 3's. The square root of 3 times 3 would just be 3 out front. I've got a pair of x's. Since we know these are positive, we can just pull one of these out. And I'm left with 2 on the inside because that's what's left over. Alternatively, if you happen to see this as the square root of 9 times the square root of 2 times the square root of x squared, you get 3 times the square root of 2 times x, which is 3x square roots of 2. You get the same value either way you do this. And then number 21. We've got 216 equals p minus 23 all to the 3 over 2. We've already got the weird thing by itself, so what we're going to have to do is to rewrite this as a radical. So we get 216 is equal to, that tells me we got a square root of p minus 23, and that's going to be to the 3rd power. Okay, I'm going to undo this by taking the 3rd root of both sides. 3rd root of 216 is going to be 6. So we get 6 is equal to p minus 23. We're going to square both sides, and that gives us 36 is equal to p minus 23. Going to add 23 to both sides and get 59 is equal to p. And that's it. And move on to radical exponents. Starting with number 9, we've got to convert this to from radical to a rational exponent. And we have to know that square roots have an index of 2. That's going to give us x minus 2 as the base. You absolutely must include those parentheses. The 5 is going to become the numerator, and the 2 is the denominator. Moving ever onward, we got to go backwards. Here I'm going to set up my radical. My index is going to be the denominator. I'm going to put this whole thing in parentheses, and that 4 is going to be my exponent. I could also put that on the inside, and that would be okay. And then I'm going to have x minus 2. Just as a side note, if you decide to put the 4 on the inside, the x minus 2 is going to have to be in parentheses. Alright, looks like number 13 is up next. Here we've got to simplify a square root. I'm going to write this as, look for perfect squares within 27. I know it's 9 times 3. That's a good sign because I know that the square root of 9 is going to be 3, so I can bring that part out front. The other 3 is not going to have anything to go with. Okay? Then we've got x. I'm going to rewrite, and by the way, x doesn't have anything to simplify with, so I'm just going to rewrite that inside. I'm going to rewrite y cubed as y squared times y. And since we're assuming that these are all positive, y squared can just come out as y. And we have 1y left over. So I'm going to box the things that took out. We're left with a y afterwards. Nothing else here in video. All right, here we go. Okay, let's get our rational exponent expression by itself. I'm going to minus 4 to both sides to get 81 is equal to this thing. At this point, I'm also going to convert this to a radical to make my life a little bit easier. So it's x minus 3 on the inside. And then we've got the 4th power on the outside. I'm going to start off by taking the 4th root of both sides. I want to get rid of that 4th power. The 4th root of 81 is 3. You can do that in a calculator, or see that 3 times 3 times 3 times 3 is 81. And that tells us that we have the 3rd root of x minus 3. I'm going to cube both sides to get rid of that radical to get 27 is equal to x minus 3. If I add 3 to both sides, we get 30. All right. Now we got the new stuff, exponents and logarithms. Oh my, this is going to be the first time that we see this. I'd like to talk about 2 different ways for us to graph these. I will do the first one in red for the log, and then I'll do the second one in, let's say, blue for the exponential part. So for the first one, I'm going to talk about this in terms of rewriting this as an exponent. We know that we have logs or some exponent written as log base b of what we call the argument. So what we do to rewrite this would be take the base to the exponent, and that's equal to that argument. So when we do that, that's going to be 3 to the y is equal to x plus 1. If I minus 1 to the other side, we get 3 to the y minus 1 is equal to x. There are a couple things we can get from this. The first is that the last number here, in this case, -1, is going to be the asymptote. Because we're dealing with 3 to the y, it's going to be a vertical asymptote. And then I'm going to plug a couple points in. So if we've got an xy table, I'm going to plug in y values. If I plug in 0, 3 to the 0 is 1. 1 minus 1 would be 0. So we get 0, 0 as a point. And then I might plug in like 1. 3 to the 1 is 3, minus 1 is 2. So we get 1, 2 as a point. And this graph is going to look something like this. The alternative to graphing these is going to be based on the mother function. If you ever need me to draw a mother function for you for these, I'm happy to do so. The mother function for this graph is going to be in blue here. And for the text thing, which is fun, that was not my intent. I'm going to try to get rid of that now. And now I added another one instead. This seems fun. I'm going to pause this as soon as I can get out of this. Okay, back with you. So now we've got our function for the exponential. I'm going to add in my horizontal asymptote for the mother function. And we've got a couple of points at 0, 1, and 1, 3. And then we're going to look at this in terms of transformations. The minus 4 here means everything is shifted down 4. And here means that we're going to have points that are twice as far apart from where they normally would be. This is always going to be based on the asymptote. So if we move the asymptote down 4, that would then be at -4. And then if we take this point, which used to be 1 above the asymptote, now it's going to be 2 above the asymptote. So what was 1 is now 2. Okay, and then the point that used to be 3 above the asymptote would now be 6 above. So 1, 2, 3, 4, 5, 6. And our shape would be the same and look something like this. I find it a little bit easier to work from asymptotes and plugging in points. So you know the asymptote's going to be at -4. You can make a table for x and y and plug in a couple points for this. But since we've talked so extensively about transformations, I want that to be open to you as well. Ooh, that's fun. I guess that disconnected from here. Cool. Okay. I actually have to go a little bit further up. Fun. All right, this is number, whatever this number is, it's not numbered, is based on the idea that exponents and logs are inverses. Since they're inverses, all of their points are going to be the opposite. So instead of 0, 1, it's going to be at 1, 0. Instead of 1, 2, it's going to be at 2, 1. And instead of 2, 4, it would be at 4, 2. And that's it. That's all this is. For the next one, we're being asked to convert between log and exponential. So this is based on the idea that if I have a base to some exponent is equal to some answer or argument, then I can rewrite this in log form by saying log base b of a is equal to e. It's helpful sometimes to treat things just as exponents, and this is a great place where we'd see that. So here we'd have my base is b, so that would be 3. My exponent would be 11, so that would be 3 to the 11, and then I've got equals x, and I'm done. For the bottom, I've got to convert it backwards. Here my base is 2, so this is going to be log base 2. My argument or answer is 11, that goes on the inside, and then my exponent would be 3x. Just switching these things around. For evaluating logarithms, we got two ways to think about this. What power of 2 would be 64? Or I could convert this to a exponential expression. So we get 2 to some exponent is 64. And if you'd like, you can guess and check. And you're going to find out that that exponent is equal to 6 because 2 to the 6th is 64. For the last one, here we've got log base 2 of 1/8. And kind of similarly, I'm going to write this as 2 to the exponent is equal to 1/8. I know I've got to flip this. It might actually be a little bit easier for me to rewrite the right side this time. So I could say this is 2 to some exponent. I know this is going to be 1 over 2 to the 3rd, which I could rewrite as 2 to the negative 3. That means that this would be e is equal to negative 3, so negative 3 would be there. And that's all we did for this. Let's call it a day.